Alright guys, in this video I'm going to work out and show you one more time how to do each of these different application problems that we've learned in chapter 16 so that you'll be prepared to do them on the test that's coming up. So this first section is labeling the conjugate pairs, and I've written over here the suggested steps and a little reminder of how to do it. The first thing that I would do is identify the conjugate pairs. So you would pair up one reactant with one product and then the other reactant with the second product. And then once you do that, you'll figure out which one's the acid, which one's the base, that sort of thing. But back with the conjugate pairs, they differ just by a single H and also a positive charge. So you want to match up the two formulas, one on the reactant side, one on the product side, that are almost identical, but one has an extra hydrogen. So if I focus over here on this acetic acid, I need to figure out, is it going to become the H3O or is it going to become the C2H3O2? And whichever one it's going to become is the one that I'm going to pair it up with. Now, I know that the pairs need to have almost the same formula. The only difference is a single hydrogen. So the only option here is to pair up that acetic acid, oops, got the wrong thing, with the C2H3O2, because those two formulas look almost identical. The only difference is that this one's like missing that H. So if you could add in an H and make them look identical, that means that you should pair them up. And that would mean that the H2O and H3O have to get paired up. Again, their formulas are almost identical, but one has one more H than the other. All right, then we're going to have to focus in on like one pair at a time and figure out if the reactant is an acid or a base, and then we'll be able to label everything else pretty easily after that. So the acid is going to be one of the reactants, and you're going to look at what happens to it by the time it gets over to become its conjugate. So the acid is the reactant that will lose an H by the time it becomes its conjugate. The base is going to be the reactant that gains an H by the time it gets over on the other side. So looking at my C2H3O2 and looking at what I've paired it up with, by the time it gets over here, which is going to be the conjugate, remember that both of the products are going to be labeled conjugate. Either one's going to be a conjugate acid, one's going to be a conjugate base. So by the time this acetic acid gets over here to its conjugate form, it has lost that H that it had in the front. So this formula is going to end up donating an H, which makes it an acid, a Bronsted-Lowry acid. And then our definition for a Bronsted-Lowry acid is that when it does donate its hydrogen, it becomes a conjugate base. If you look at what happens to the H2O, by the time it gets over here, it's going to add an H or gain a hydrogen, and that's what bases do. Bases end up gaining hydrogens, and once they do, we call them conjugate acids. The conjugate that it becomes is an acid. So one quick check when you're doing these problems. You have kind of a few different pairs going on. We have a pair of reactants, we have a pair of products, and then we have the pairs that we've created, one reactant with one product 2 times. So in each of the pairs, you should have one acid and one base. You never put 2 acids together or 2 bases together. So the 2 reactants have to be different, one acid, one base. The 2 products have to be different, one acid, one base, so they'll both be called conjugates. And then within a pair, you have one acid, one base, one acid, one base. So never put the same word together in a pair. All right, I want you to pause the video and try the next 2. I'm going to pause my recording and fill in the answer. When you resume, you'll have the answers up on the screen where you can check your work. All right, here's the answers for you to check. On the first one, I paired up the HSO4 with the SO4 because the only difference is that one hydrogen is missing. And then same here, the H2PO4 and the H3PO4, the only difference is the number of hydrogens. So that's where I got my pairs. And then I can see with this middle pair, the H2 to go to the H3, it has to add a hydrogen or gain a hydrogen. So we label the H2PO4 as a base because it's about to gain a hydrogen. We label the HSO4 as an acid because it's about to lose its hydrogen or donate a proton. That makes it an acid, becoming a conjugate base. All right, let's review how to do the next section, which is naming acids and bases. We had mostly, spent a day last week learning how to name acids, and the basic idea is that the name of the acid comes from the name of the anion, or the part of the formula after the hydrogen. So focus on the part of the formula after the hydrogen, and you need to come up with the name of that anion. So the name of PO4 would be phosphate. And if the ending is 8, like this, then our name is going to basically just replace that ending with an IC. So that would seem to be phosphoric acid. That might be something tempting for you to put, which isn't quite right. Phosphoric acid or phosphate was one of the exceptions. We add back in a syllable from the phosphorus element before we put that IC ending, just to make the word flow a little bit better, and it ends up becoming phosphoric acid. If you were to put phosphoric acid on the test that's coming up, I probably wouldn't count off for that, since it's a little bit of an exception to get used to. All right, on number 5, again, we're looking and focusing at the anion, and we want to come up with the name of that anion. And it's just the element chlorine, but when chlorine is in a compound like this, it ends in "ide," chloride. So when our anion ends in "ide," which again, it will, anytime you have a single element, we're going to have an extra piece to our name. We're going to start our name off with hydro. We don't use that hydro prefix when it ended in "ate" or "ite," but we do when it ends in "ide," when it's just a single element after the hydrogen. And then we put the basic part of the name here, but we're going to replace the "ide" with an IC, so it becomes hydrochloric. And then any acid is going to end in the word acid. All right, on this next one, I'm focusing on the anion, and C2H3O2 is acetate. So I can see that 8 ending, once again, that's going to become an IC ending. So it becomes acetic, and then we add the word acid. This last one is not an acid. I can tell it's not an acid because it doesn't start with a hydrogen. There's no hydrogen at the beginning, and acids always start with a hydrogen. I can also tell it's not an acid because that OH is an indication in this chapter that we have a base. So for a base, there's no special rules for the naming. You just name the first ion, and then you name the second ion. So that would be sodium for my first ion or first piece of the formula, and then we know that hydroxide is the name for OH. So this is just sodium hydroxide. All right. The next section is actually a really easy question. It wants to know if each acid is monoprotic, diprotic, or triprotic. And I remind you of the key to answering this question right here. You're just looking at the subscript of the hydrogen. And I'm talking about the first hydrogen in the formula, the H at the very beginning of the formula. If there's another H, don't worry about what its subscript is. Just look at the H at the beginning. So I've got a 3, a nothing, which is an understood 1, another understood 1, and a 2. And that tells me what my answer is. If it's got a subscript of 3, it's triprotic. Subscript of an understood 1 is monoprotic, and subscript of 2 is diprotic. The last problems that we'll look at in this video, and then I'll switch over to a new video just to break it up for you, is sections 12 through 14. This really comes straight out of our notes. It came from the lesson on the self-ionization of water, and we had a definition for a neutral solution, acidic solution, and basic solution that focused on comparing the hydronium ion concentration, that's what that symbol means and the hydroxide ion concentration. So if you look at your notes over that self-ionization of water section, you'll see what these are. In a neutral solution, they're equal to each other. In an acidic solution, you have more hydronium than hydroxide, so it's greater than. In a basic solution, there's less hydronium than hydroxide. All right, I'm going to switch over and start a new video to work out the remainder of the review sheet.